Welcome to The Explainer. Today, we're tackling a material that is notorious for being demanding, but when you handle it just right, it delivers absolutely unmatched results. We're talking about polyphenylsulfone, or PPSU. For engineers and product designers, PPSU is basically the ultra-high-performance diva of thermoplastics. It demands absolute precision on the shop floor. But, as we're going to see, the payoff for following its strict rules is a component that can survive some of the most extreme environments on Earth. Let's get right into it.
Now, you might be wondering, why even bother with such a demanding material? Well, you just have to think about one specific number, 1,000 plus. Properly molded PPSU components can survive over 1,000 autoclave sterilization cycles. We are talking about repeated, brutal exposure to saturated steam at 134 degrees Celsius, and it still retains over 90% of its mechanical properties. To put that into perspective, your standard polycarbonate starts degrading after just 50 to 100 cycles. It's a massive difference.
What's really fascinating here is the sheer physical dominance of PPSU compared to its peers. When we measure notched ISOD impact resistance, standard polysulfone sits at about 70 joules per meter. PEI, or Ultem, sits at 55. But PPSU, a staggering 690 joules per meter. It literally has nearly 10 times the impact resistance of standard PSU. No wonder it's the go-to for medical reusable instrument trays and aerospace components where structural failure is, well, simply not an option.
So here is our roadmap for today's explainer. Number 1, meet the material. Number 2, the drying mandate. 3, precision temperature control. 4, pressures and flow. And 5, troubleshooting.
Section 1. Meet the material, the ultimate thermoplastic.
To really grasp why PPSU processes the way it does, we kind of have to look at its chemistry. Its molecular backbone is built around phenyl rings bridged by sulfone groups, and this brilliantly illustrates why it's so tough. That highly specific chemistry delivers extraordinary thermal resilience and broad-spectrum chemical inertness. It handles highly aggressive hospital disinfectants, aliphatic hydrocarbons, you name it, even aviation fluids. But here's the catch. That same robust molecular structure means it requires an incredible amount of energy, meaning serious heat, just to melt and flow.
Moving right along to Section 2, the drying mandate, the non-negotiable first step.
I want to get a bit serious for a second here, because when it comes to PPSU, proper drying isn't just a best practice. It's a strict law of physics. Listen to this rule. A standard hot air oven is insufficient. Always use a desiccant-based closed-loop dryer. Why is that so absolutely crucial? Because PPSU is incredibly sensitive to moisture at high temperatures. Even a tiny, microscopic amount of moisture at processing temps above 340 degrees Celsius causes hydrolytic chain scission. That literally means the water molecules chop up the polymer chains, completely degrading the molecular weight and destroying your part from the inside out before it even leaves the mold. So the takeaway here is following these exact mandatory steps. Step 1. You must use a desiccant closed-loop dryer to achieve that low dew point you need. Step 2. Set the heat to between 150 and 165 degrees Celsius. Step 3. Run it for a minimum of 4 to 6 hours. And Step 4. Verify. You absolutely have to verify that the moisture content is below 0.02% by weight using a moisture analyzer. If you skip this, you're looking at severe mechanical degradation, splay marks, silver streaks, and ultimately a completely ruined batch.
Okay, let's dive into this next critical phase. Section 3. Precision temperature control, navigating extreme heat.
Once your resin is perfectly dry, you've got to manage the extreme heat required to mold it. Listen to these parameters, because we are operating in a very narrow, very hot processing window. The rear zone starts at 330 to 350 degrees Celsius, and it steps up to 360 to 380 degrees right at the nozzle. You really have to thread the needle here. Drop too low, and that high viscosity melt won't fill the cavity properly, which gives you poor weld lines and dangerous internal stresses. But if you exceed 400 degrees Celsius, you induce severe thermal degradation and nasty discoloration.
And hey, it's not just the barrel that needs extreme heat, it's the mold itself. You absolutely, without a doubt, must use an oil-based temperature controller. PPSU requires a mold temperature between 120 and 175 degrees Celsius to allow that thick melt to flow into fine features before it freezes up on you. Those standard water-cooled molds that only hit 80 to 90 degrees? Completely inadequate. Running a cold mold pretty much guarantees poor surface quality, cold flow marks, and seriously elevated warpage.
Which brings us to Section 4. Pressures, speeds, and flow. Controlling the high viscosity melt.
Let's see how all this heat translates into the actual mechanics of molding. Pushing this high-viscosity material into a mold is a delicate balancing act. Because PPSU is so thick and viscous, you need really high injection pressures. We're talking 100 to 170 megapascals. But pay super close attention to your holding pressure. It should be 40 to 60% of your injection pressure and held for 5 to 15 seconds. Let me be clear. Insufficient holding pressure is the absolute #1 cause of sink marks in PPSU parts. You'll also want a moderate multi-stage injection speed just to prevent jetting and adiabatic heating.
Now, tool design is just as vital as your machine settings. Because of that extreme viscosity, undersized gates are a total disaster. They cause excessive shear stress and localized degradation. You really need generous gate dimensions, ideally with a minimum land length of 0.5 to 1.0 millimeters. And venting? Hypercritical. Vents have to be shallow, around 0.025 to 0.038 millimeters, so you prevent flash at those super high mold temps. Inadequate venting leads to gas entrapment, triggering what's called the diesel effect. That's where the trapped gas spontaneously ignites and leaves these terrible burn marks right on your part. No good.
And finally, Section 5, Troubleshooting, the processing cheat sheet.
Think of this as your ultimate cheat sheet for when things inevitably go wrong on the shop floor. Let's talk about two really common defects, splay, or silver streaks, and short shots. Notice how they tie directly back to the exact two mandates we just emphasized. If you see splay, you failed the drying mandate. Full stop. You need to verify your desiccant dryer is actually hitting 150 to 165 degrees. Now, if you see short shots, you've likely failed the temperature mandate. Your mold is just too cold, or your injection pressure is too low.
Then we have burn marks and discoloration. As we discussed, burn marks usually mean trapped gas, so you've got to check your venting and reduce your injection speed. But pay really special attention to discoloration or yellowing. Guys, this is a massive red flag. It means your material has surpassed 400 degrees Celsius in the barrel. Not only does this permanently ruin the mechanical properties of the part, but overheating PPSU actually generates dangerous, sulfur-containing decomposition vapors. If you see this happen, you must reduce barrel set points and purge your machine immediately.
PPSU is a phenomenal material. It truly pushes the boundaries of what plastics can do, but it requires an environment that is totally uncompromising in its precision. So I want to leave you with this final thought. Is your shop floor equipment truly rated for the extreme heat and the strict drying conditions that PPSU demands? Take a hard, honest look at your desiccant dryers, your oil-based controllers, and your barrel capacities before you take on this incredible but highly demanding polymer. Thanks for joining me for this explainer, and hey, happy molding!